So today we will talk about binary search trees. The rationale behind the using a binary search tree is about how to organize the elements in a tree. Now, as we have discussed, when you are building a tree, it's quite a burden to decide which element is going to go where. So we are going to see a lot of different tree structures. Today, we are going to see binary search trees. Today afternoon, we are going to see something called tries. And in the future, I believe in the last lecture, we are going to go over some other kinds of trees that may be useful. So the point is why these different kinds of binary, different kinds of trees are out there is, you see, when we are keeping the elements, there are in the linked list, for instance, regarding this succession relation, so which datum is going to come after which datum, or which element is going to come after which element, and there is a single choice. So you can only go to a single place when you have a node in your linked list. Of course, you have multi-lists, so on and so forth. But as we have discussed, you know, there is a different rationale behind them. And even though there's a different rationale, it's still a problem in multi-lists as well. How are you going to organize the additional linked list levels? So in a tree, different from a linked list, you know, there are two descendants. There are two successors whenever you give a node. Of course, this is for binary trees. If you have higher order trees, there might be even more number of successors. But when this is the case, then whenever you want to add a new element to the tree, then sorry, when you want to add a new element to the tree, then you need to somehow find an appropriate place to make the addition. Or even if the tree structure is more complicated than you would expect, like this, okay? So let's say there is also this kind of links around here. Okay. So then if you are going to add something, where are you going to add it? So you might do it like, okay, find the first place, which is appropriate, and add it. Or you can do it like, well, according to some organization, some other logic. So first of all, what is the first empty place? If you go from left, this is the first empty place. If you go from right, this is the first empty place. And that might be different definitions, but the real problem is not that, because you can agree on a definition and you can go on like that. But the real problem is that what is the complexity of adding and retrieving if you don't have the ability to select which successor you would choose whenever you are doing things? So the worst case might be, let me draw you a small tree. Let me get rid of those. Okay, imagine this is your tree, and you have agreed on making a breadth-first search when trying to find the first empty place. So how many, you see, it's very obvious that you need to add to here, right here, but it might be a more complicated tree than that, so you don't know. You don't know what's the depth, you don't know where you are going to, how deep you need to go in order to find an empty place. So you need to start from scratch, start from the beginning, and look for every level in order to find a good place to add the node to. And if you do breadth-first search, then you need to start from here, you need to visit this node, and then this node, and then this node, and then this node, and then this node, and finally you find a null on the right child and you add it to here. Or if that was deeper, then you need to go to the deeper levels as well. So if you don't do a breadth first search, but a depth first search, then again, imagine you are doing a pre-order search. Then in what order you will be visiting those is you need to first go to, sorry, this one, and then you will visit this one, and then this one, and this one, and then this one, and then this one, and finally you will find a null child to make your addition to. So maybe you can do something like a post order. If you do the post order search, then you would first visit this one and this one, and then this one, and then this one and this one. Now you will find earlier, actually 2 nodes earlier, not very much, but even for these kind of situations, you still go to n nodes, because you can imagine that there is a whole bunch of leaves and tree in here. So then you need to visit all of those in order to find the empty place in here. Okay, so it's still ON. And we can make our, actually, a cool thing is we can calculate it as well. So you remember the recursive complexity analysis? What we were doing was, if you start with, let me do it in a different color. Let's say that this is our pre-order or post-order search, whatever you say. Then that would make 2 more calls. So this is like 2 to the Tn, right? Plus, and make the visit the node in here, plus some constant operations. So if we resolve it, that one, actually I have made a mistake in here, sorry. If you resolve that one, this one is going to be 2 times 2 to the Tn minus 1 plus 1 plus 1. So we have done this, right? You remember this kind of resolution? We have done this for the Hanoi Towers. It was quite like this. Actually, it was, what it was doing is it was, for Tn minus 1, it was carrying the smaller number of disks from one pack to another. But in here, what we are doing is we are visiting the smaller tree in that case. But you know where this goes. The complexity of this is 2 to the n. You might say that this is not this is not ON. This is not linear complexity. This is exponential complexity. But please be careful. N is here, the depth. Okay. So the depth is from root to the leaves. How many steps are there? So if this is the depth, then the depth is the, you can write it like, let's write it in a different way. Okay, so this is 2 to the h, height of the tree, you can say. And 2 to the h is, this is like log to n, and this is n. Okay. So if you think of it in another direction, it is like the complexity is 2 to the h, or 2 to the h for the depth. But how many nodes are there in here at the worst case? It is again 2 to the h. So the number of nodes n is equal to 2 to the h. So if your complexity is O 2 to the h, then it's the same thing as ON. Okay, in terms of number of nodes, of course. So the story here is you need to if you don't know which way to go in your tree, if you don't organize your tree in using such a preliminary information, then you need to visit every node in order to make something meaningful. And that means it's useless, at least for searching purposes. But of course, we know it's not useless because we can organize it. And how you organize it makes the difference. And there is one of these organization approaches is something called binary search tree. Binary search tree. So binary search tree comes from binary search. Okay. So, well, maybe you can think of it like it's a binary tree, but it's used for searching. I don't know which one would be better, but it mimics binary search, something called binary search, by using a tree. So let me tell you about binary search. It's a very simple algorithm. Okay. Suppose you want to, now we won't be talking about searching in this lecture a lot, but it's an issue about algorithms. So you will sooner or later come up with it. So let's say this is our array and you want to search for something. Search I, or better yet, search n. So what you do in binary search is when your array is like that, first of all, you assure that your array is sorted. So your array should be sorted. Okay, if it's not sorted, then actually there is no efficient search algorithm. So if you have an unsorted array, your worst case complexity is O(n). You need to look for every element in the array. So you can think of this phenomena very close to what I have just explained you. Okay, so it's like if you have an unorganized tree, you need to look for every node in the tree in order to find something. Okay, even when you're adding something, actually you are trying to find, searching for a space. So adding can be thought of searching as well. So if you're searching for something in an unorganized data structure, then you need to look case by case. Then the complexity is O(n). Just like this. In the array, if you have an array and if your array is unsorted, then you need to do n operations. Your complexity is O(n) when searching for something. And if your array is sorted though, now you have an information about how to look for things inside your array. What you can do is you can start from the median. Okay, so the median element is, of course, according to the indexes, and you will look at how many elements there are. Let's count. 1, 2. Let's start from 0. 3, 4, 5, 6, 7, 8, 11, 12, 13. Okay, there are 14 elements in here, and how you begin is you begin from the middle of the list, or I can say median. Well, now if you have odd number of elements, the median is easier to find. If you have an even number of elements, you have 2 candidates. So that might be 6 or 7, right? If you choose 6, there is going to be 1, 2, 3, 4, 5, 6, 7 elements on the right, 1, 2, 3, 4, 5, 6 elements on the left, and if you choose 7, vice versa. And in this case, it doesn't matter. You can either choose one of those. Okay, you choose this. So let's search for 38 first, or let me choose a better number, 29. Okay, I'm searching for 29 in here. So when you start from the middle, you know something. All the elements on the left are smaller than 29 because the element that you've been looking now, 15, is already smaller. And since this array of yours is sorted, the elements on the left should be also smaller than 29. So what you're looking for is not on the left-hand side. That one might also be larger than 29, and in this case, the right-hand side would be useless. So you eliminated at once half of the elements. And what you do next is you get the other half, this half, How many elements are there? 1, 2, 3, 4, 5, 6, 7. And you choose the middle, 30. Now 29 is smaller than 30, so you need to go to the left. You can ignore every element on the right-hand side. So you see, you again eliminated the other half, of the element. So the quarter of the elements is gone. So in each step, so this is gone. Okay, this is already gone. So what you need to do, actually, you can put 30 as well in the going theme. So what you have now is 3 elements, and you start from the middle again, 24. Now 29 is larger than 24, so you can ignore these. And at the very last, you have only 1 element. And this should be equal if 29 is inside the array, but it's not equal. So we can deduce that 29 is not in the array. So you see, every time we select the medium element, we divide the array to half. And we eliminate half of the elements from our perspective. So how many times can you divide something in half? It's all, of course, logarithmic complexity. So this is, sorry. So binary searches complexity is log n. Of course, there is also the sorting sorting cost, but you can think of it like this. Please don't think of a single search. If you are making 1 million searches, then you can give away the cost of sorting the array, right? Because you will do sorting once. Now, how is this related to binary search tree? What we are going to do is we are going to carry the sorted arrays structure into a tree. So how will it look like is, first of all, you are going to have a binary tree. Of course, it's going to be binary. And whatever in this binary tree, whatever the node you choose, it doesn't important which node you choose. So you might, let me make a bigger tree, okay? So we might choose this node. And let's say there's an element in this node, and this is 5. The left-hand side subtree, so all the elements inside the left subtree, not just a single element. All the elements inside the left subtree should be smaller than 5, and all the elements in the right subtree should be larger than 5. So let me draw this in a better way. So there are 2, 4, 6, 7 elements. 1, 2, 3, 4, 5, 6, 7. Okay. So it's like 5 is in the middle, the median of the array. It's like thinking like this. So if you think about 5, all the elements on the left-hand side are smaller. All the elements in the right-hand side are larger. So if you think about this, all the elements in the left subtree are smaller. And if you think about right, all the elements in the right subtree are larger. And the important thing is, it is independent from which node you choose. So we have chosen root, but any other element that we choose is going to obey the same rule. So if we can put 8 in here, so the left and right-hand sides will be smaller and larger than 8. But please be careful. The left-hand side of 8 should be smaller than 8, but this node is also in the right subtree of the root. So it should be larger than 5 as well. So I cannot write here 3, because 3 is smaller than an 8 trace, but it's also smaller than 5. It should be larger than 5. All right. So this would be something like anything between 5 and 8. Of course, it might be 6 or 7. I think this one should be smaller. Let's make it 6, and this one should be 10, or something, anything larger than 8. And on the left-hand side, if you choose this one, this should be smaller than 5. Let's do it 3. And 3's left child should be smaller than 3, but also smaller than 5, which is okay. So something smaller than 3 is also smaller than 5. But the right-hand side, it should be larger than 3, but smaller than 5. If you're talking about an integer, then we only have one possibility, 4. Okay. So if you do this now, you can do the search by the same way you make the organization of your tree. So suppose you are searching for 7. Okay, is 7 in here or not? So what you would do is you would start from the root. 7 is larger than 5. You go to the right? Because you see, I'm in the root, I'm in a node, I'm looking for some value which is larger than node. Then I should go to the node's right subtree. So you see, I am eliminating all the elements in here, just like in the binary search. The left-hand side is gone because it only contains smaller elements than the root. And what I do is next I go to here. So I compare 7 with 8. And it's smaller, so I need to go to the left. Okay. And 6 is smaller than 7. So my next comparison will be with 6. 6 is smaller than 7. So I need to go to the 6's right. But you see, there is no right child. So I can deduce that 7 is not in the tree. Just like the previous example I have given you about the search binary search trees. Now, likewise, you might be adding 7 as well. It's the same as searching. So you do all the same operations when you are adding 7 instead of searching for 7. But the only difference is when you find the null child, which means that, okay, I have traveled to one of the nodes, but there is no node with the data that the data I have been adding should be. So if there were 7 in the tree, it should have been in this point, but it is not. So I should add it to here. Okay, so what you do when you are adding something is you search for it and find the place that it should have been and put it in there. So there are some properties of binary search trees which we are going to talk about. Actually, everything is not very good, and using a binary search tree depends on some circumstances to be advantageous. But if you say everything goes well, then the complexity of searching something and adding something to a binary tree is all log n, right? Because when you are adding something, you should go log n steps, the depth at worst. And if you are searching for something, again, you should go at most depth steps. All right. So this is very advantageous. So adding and searching in log n steps, that's very good. And also when you are, also there is a preliminary assumption that you do when you are searching a binary, when you are using a binary search tree. There should be no duplicates in the binary search tree, because if you allow duplicates, then you break your intuition, then you break your logic. So let me give you an example. Okay, now it will take too much time to search for an example, but the intuition is now we have added 7 to this tree. If we want to add 7 one more time, then it would be in the same place, right? I need to add it in the same place. It cannot go any place else. So if I want to add 7 on the left subtree, it's not possible because 7 is larger than 5. If I want to add it to the right subtree, then it would not be on the right side of 8 for sure, because it's smaller than 7. So you see the address, there's a single address that you might do the addition. There's only the the right child of this one. Okay, so it needs to go to a single place. There's a single place that you can add when you are making the addition. Well, of course, you can design some tree which doesn't conform to binary search tree, but then that would not be a binary search tree. So the deal in here is the duplicates are not allowed in binary search tree. So when you are talking about a binary search tree, at least what you how you build your searching, let's call this index, how you build your searching index should not allow duplicates. Okay, so please give me 1 minute. Okay. So, well, actually, this is the thing about binary search trees. This is how you organize and use a binary search tree. But there are a lot of details, of course. First of all, implementing the searching addition, these are something we need to do. And also, you see, it's not the only thing that you do in the search tree will not be addition. You would do removals as well. So you can take a binary search tree and remove something from it. And we will handle those situations. And we'll talk about how complicated removal can be. And also there is a bad situation about binary search trees, which we will again talk about. So these are the main concepts about a search tree. Okay. If you have any questions, I can take them now. All right. So let's do the coding then, okay? So let me move on to my other computer. And share my screen. All right, so first of all, we need to make we need to design a structure, a node structure, and a tree structure. So it's actually is not very different from the binary trees. But nevertheless, I will be giving the node a different name, BSD node.h. Why not do it regular node? Okay, I will do it next. And let's make this new file tree.h, and let's make this okay. And why am I doing now? Why did I change my mind from BSD node to normal node? Is I'm going to show you two different implementations, and the second one we are going to discuss it. But the second one is more appropriate for calling it a BSD node. So this is the real logic that I'm going to use here is I'm going to put it in the tree code. That's why node is not very related, dependent to the tree that I'm building. So this should be class node. And let's do it over now. This time I will do it with integers. Okay, so node star left and node star right. And let me constructor. And let's take integer inside the constructor. So let's construct the node with the data. And let me write the code for the node as well. Okay. So this in here we have equalized the parameter with the classes variable, and I also need to make the left and right node. Okay. So I think in order to use null, I need to put and for the node, again, I need to have setters and getters. So let me write set left, void set right, and void set data. Well, I won't be using set data a lot, but let me write it in case I need it. So these will be taking node star as parameter. All right. And also there will be getters. So there would be like node star get left and node star get right and integer get data. Okay, so this is almost like an automatic code generation for me. So as you write more and more of this kind of code, you will it will be more on the spine, not on the brain. Okay, so since this is not star left, do this right, and that will be the data. So I'm not thinking about the destruction yet. I will do it right after I make the construction. So and the addition. So I need to, in order to think about the destruction, it is more solid if I have a already built tree. Okay, so I can think about it and show it to you right now, but it wouldn't mean a lot because I would not be able to give you the example. So again, I'm leaving destruction to a little later, but we need to write it without forgetting about it. Okay, so it's important. I'm leaving to the later parts because the order, natural order of things requires that. Okay, so these are my setters. So let me do my getters. Return this. So you see these functions. Oh, I have a typo in get right. These functions, well, actually, they are only making delegations. So they are just, you might be asking yourself, well, what is the point in doing this if when I can make these public? Why don't I do this public? Well, you can do this public, of course. And if we are talking about the context of our homeworks and our practices in school in here, you don't need to do anything public, okay? So anything private, you can do everything public. But the thing is, it is good that you get used to information hiding, because even when you are coding in real life, even when you don't need the member variable to be private, so making it public doesn't change anything, and even it's more advantageous. but you don't know what is going to come in the future. So now I am not using such an IDE, but now making just a single right click, you can add all the constructors, destructors, anything at once. Let me show it to you. Why am I? So let me show you one thing. You can also do it with Visual Studio, and there are other cool features of it, but let me show you something. Of course, this is going to be from Java, but you can take the similar, you can have similar functionality in other programming language IDEs as well. So let me now put here a new class. So let's call it a person. Okay. And let's say I have private string name and private string surname. Okay. And when you right click, and that's all, yeah, here it is generates, and it asks you what to generate. So you can say generate me getters and setters, and select which for which member variables you are going to generate getters and setters, and say okay, and bam. Okay, all the things that we've been writing is actually generated at once. But of course, this I made another typo. So. And also you can generate constructors as well. So you can say generate constructor, which variables I should take as parameter, it asks. So take both of them as parameter, and it gives you, generates you this code. Okay. So maybe you remember we always, we sometimes write to string. You can even generate something like this. So you say generate to string, and transform these to string, you say, and plum generates the code. Okay, so most of the time IDEs do that. So it's not much of a burden to make things private. So it is good to get used to using private variables, and even it's not a bad practice to make everything private. Every not function, but every member variable, making them private is not a bad practice. It's something good. Of course, there might be some cases where you need to use static constant variables, things like this. Of course, then you need you do what you need to do. But for ordinary class variables, you can always prefer to do this, to do those private. Okay, enough chat. Let's have a look at this. These are okay. This left, this right, this data. Now I can move on with my trees. And the real deal, which I'm going to do, is I'm going to do it in the next lecture, actually. But so I need to have the definition of a node, of course, and there is going to be class tree of mine. It's going to contain private node star root and public tree. Let me do this in here. So root should be null. All right, so this is the skeleton for our binary search tree. There's nothing that we have done regarding using a binary search tree, but we will start doing it now by making an addition. So as you remember, what we have done is we have seen to add something according to the node's value. So what we will do is we will iterate over the tree, and we will search the tree until we find a null. And when we find a null, it is the place for our data to go. If we cannot find a null, or if we directly find the data that we've been looking for, then we won't be adding that to the tree, because It's already there. So let's do that. So let me put an add function in here. Now, I will do this void in the beginning, but we will talk about this. Okay, so void add, and there's going to be integer in here. Okay. So let's do this now. We have integer data. And first we need to construct the node. So node star n equals new node data. Okay. So now we've got a node. Don't we have node hash here? So now we have a node pointer, okay, which points to the node. What we will do is we should first check the empty tree. So if root equals null, then I should do root equals n and then return. So if my tree is empty, so let me do it like this root. All right, it also works if you don't write it, I think, but so yeah, since we use the same name with the previous code, it gets confused and gives me the my previous functions. Sorry for that, but yeah. We might give a different name, but I think this is more elegant, so I'm going to use this. Okay, so this is empty tree addition. And then what we will do, what we'll write is in here is going to search for every possibility. So what I'm going to do is I'm going to write the code directly now and then give a break. And then when we come back, I'm going to show it to you by drawing once more and then go over the code again once more. So what we need to do is we need to have a temporary variable, which is going to start from the root. Okay, and while temporary variable is not null, I am going to iterate. And how am I going to iterate is if temporary variables get data is larger than data, I'm going to do something. Else if the temporary variable's data is smaller than the data, I'm going to do another thing. Else, the only possibility left is they're equal. I'm going to do another thing. So if the temporary data is larger than the temporary data is larger than the data that I'm trying to add, what will I do is, well, I need to go to the little left, right? So yeah, because what I'm adding is smaller than the node I've been looking for, then I need to go to the left of the node. So it's the node is, let's think about it with real values. The node is 10, the data is 5, let's assume. So where I need to go to the left. So I would say temp equals temp get left. Okay, and else what I will do is I will go to the right. Okay. Else, if they're equal, I would do nothing, return, because it's already there. And now I made the navigation, but I didn't do the addition yet. So I need to somewhere make the addition. So there's also a catch here. I'm going to the left, but I don't know if there's a left, right? Because I go to the left, but if the left is null, what is going to happen? Well, it will break out of the loop on the next iteration for sure. But if the left is null, I do know one more thing. I do know that I actually have find my place. So why don't I check it and make the addition right here? If it equals null, then let me temp set left with n, right? And then likewise, if this one get right equals null, let me add it to the right of the temporary. Well, I think that does our trick, right? So what we do is we traverse inside the tree. So you see our traversal is pre-order, right? I think so, because we first check what we do actually, we make the check in here. So this whole check is visiting the node, and if something happens, we go to the left child. If it doesn't happen, we go to the right child. No, it's not actually a traversal. We cannot say pre-order because we don't go to the half of the tree if some condition doesn't apply. So it's not actually some traversal. But what we do is we check the value and we navigate inside the tree. Let's call it navigation. And when we find an appropriate place, we add. If we cannot, we don't. So it's that simple. Let's see. Let me make some additions in here, and let's see how the tree looks like. So five. I didn't write my destructors yet. I'm going to come to this. So let me stop in here. So let's say, yeah, I need to include the tree as well. Okay, so let's add 8, 3, 9, well, and 2. Okay, let's see what happens if I run this. All right, null checks. I wasn't able to. Yeah, but I already included. Should I need to do using? I think I need to do that. I also forget to add those. Okay, did I do it in here? Yes, let me get it one more time. .cpp. Standard should be stdlib. I think it should be capital. That's why. Size is at 18. Okay, now it works. All right. So let's see if T is what we imagined like. So in the root there is 5. In the left there is 3. In the left of 3 there is 2. and the left and right is null, and the right of 5 is 8. The left is null, the right of 8 is 9. Yeah, that looks like what we imagined. So let's dig deeper into that. What happens, how we are doing it, and let's debug it. So let me draw what's going on in here, and then I will go back to my coding example. Actually, there are one or two flaws in it, so we will a couple of flaws. We will correct them as well. But sometimes, not all the times, most of the times I do it by mistake. But sometimes I do the mistakes from a pedagogical reason. Okay, because in order to not make things more complicated than it needs to be, so that you can understand, I leave things, some details later in my implementations. However, that happens very rarely. So whenever you see a mistake, please don't be frightened to say so. So yeah, what happens is in the initial phase, I don't know if there is some need to draw it, but our root is null, and whenever we add something, we add it to the root, so it goes like 5, and then we make some additions. What we do is, for instance, in this, in our particular example, what did I add is I added 8, 3, 9, and 2. Okay, so when I add 8, first of all, just like we have discussed for the linked list, I take a copy of the root pointer and call it as temp, and then I start looking for the place to add. So 8 should be in the right subtree. So I look at the right subtree. There are no right subtrees. So whenever I find there are no something, I directly add my data to there. So when I check to see that right subtree is null, then I add my new node there. So afterwards, I add 3. So this time I check the left subtree and I see that it is null. So what I do is I add 3 to there. And the next thing to add is 9. Now for the 9, I again take a copy of temp. I look at the right subtree because 9 is larger than 5. I see that it's not empty now, so I iterate the temp over to the right subtree. Right subtree is the root. And then I check again. So 9 should go to the right of the 8. It is null, so I make the addition. And then I add my new node to there. But the next one is 2. So I start from the copy of the root again, and then I check, and let me put it over the other side, so because it will be easier now. Okay. So I check the root's left side because 2 is smaller than 5, and I see that it should go left, and I iterate the temp to 1 left. And the next thing I do is I check the left of 3, which is empty, so I add 2 there. Okay, and that's all. If I were to add something like 4, then it would go like temp would start from here. And then I check 4 should be on the left of 5, and I iterate t to the next. And 4 should be on the right of 3, so I add because it's empty. So now there are 2 issues that we need to discuss. The first one is I have made a mistake in my code. Well, I left it to discuss now because when I start adding something, I do something. So let's assume that I am going to add 10. What I do is I first make a node of 10. Okay, and I keep it with n. And then when I'm searching for the place to add, what I do is I do t, and then I make this move down, and then I make the 10 connected to the right of the 9. But what if I try to add something which is already there, like 9? What's going to happen is I'm going to go to here. I will iterate my t once to the right, once more to the right. So it will show this. Now, when I find 9 is equal to 9, I directly return from the function. It's better if I delete that. Okay, so that is my mistake. So one mistake is this. The other one is not actually a mistake, but it's something that we shall discuss. The other thing is what will happen when after I add? I just go back. And is this the desired behavior? Should it be like this or not? Well, so sometimes it might be better if you just return the node that you added the pointer to the node that you added inside your tree. Why is that required? Well, I don't know, because user might require to know where their node is. Maybe they require to know who the parent is. By the way, there is no way to find the parents currently in our current structure. So if I add 1 in here, and I return this pointer, then I cannot actually find anything about the rest of the tree, but I can traverse the tree and I can use this pointer to do something about it. So I can write a function which goes inside the tree, find the father of this, blah, blah. Or I can redesign my node structure that then I'm going to have parents links as well, which can be done. It's not incompatible with our definition of a tree. So you can add another link in here which shows the parent, which we might do today, but not right now. But then again, it's no different than searching for the data inside the tree, right? So if you give the node or not, it doesn't matter a lot. And giving the node pointer, node structure back to the user is quite confusing. We have discussed this, as you remember. So what can we do? Now, I'm not going to do anything about it, so it will be void. So if I add, I add. If I can't, I can't. We might return a Boolean value depending on if the value is already inside the tree or not. So if we are able to add, we say true. If it's already there, we say false. That is also another possibility, which is questionable, right? So you might need it, you might not. It changes, but it's possible. It's not wrong. And what else you can do is, there's also, you can use an abstraction of some place in the data structure that you use. And we have seen this as well. You remember there's something called an iterator. So iterators are the abstracted away version of these things. So I don't want to give away the details of my implementation to user. And also sometimes maybe I want to return the user the exact place where some value is in my data structure in the purpose of iterating or something else. Then instead of giving away the details of my inner structure, I should, because I can need this for every kind of data structure, I can abstract it away. And it's already been abstracted away for the standard template library using iterators. You can write an iterator for this one as well, but this is not exactly related to what we are doing right now, so I'm going to skip it, but you can research it. It's possible that you do, or you can make your own iterator as well. So this is another discussion, but what I'm going to do is I'm not going to do anything. I'm just going to return void. Okay, let's see. So let me share my screen. Okay, what was I doing? I was doing like, I was talking about this, yeah. And here, instead of returning, I should, it would be better if I also delete n. Delete n. And I also talk about the return type, void. If I made it node star, then I would do like return root in here. I would do like return in here, return temp kind of thing. But now I'm not doing those. I'm skipping those. If I do add, I do add. Okay. The user doesn't need to know anything. He can always search and get the result. Now, in order to list the elements inside the tree, let's use our previously defined traversal algorithms, right? So let me open up this and copy paste those. Where are they? Yep, there you go. I called it tree nodes. That's fine. So instead of tree, if I call it something else, that would be fine. Should I do it? Yeah, better do it. Let me call it binary search tree. I'm using a naming like a weird naming like this because I am keeping BS tree to the next coding session that I am going to do. So let me rename this as well. Binary search tree, bins tree. Let me change those as well. This should be okay. All right. So I think it works. Okay, so let me copy paste those code now. So that should be. Now the destruction might be the same. Okay, so I don't need to rewrite my destruction code. Let me get this. Normally, now there's another lecture for you about the object-oriented programming. Normally, I am copying pasting this code, but if you are doing this, it's a sign that you might be using inheritance instead. Okay, so you don't know what inheritance is probably right now, but when the time comes in the object-oriented programming, you will see that you can actually, if you have a lot of common code between a couple of classes, you can build a hierarchy out of that, a class hierarchy. So you don't need to copy paste code over and over again like this. And if you check your book, there is also some explanation about it. But in our current context, we don't need it and we don't use it. But it will come someday in front of you. Let me copy paste now. So I don't need constructors. I need the destructor. I don't need recursive constructs. That's my best tree. Put them there. I don't need recursive construct. I need post order pre-order traverse. I need in order traverse. I need post order traverse. I need all of those, and I need breadth first. Print breadth first. Okay. Let me take this so I can see what my tree looks like. Okay. So of course I need to change all the names. Since I use the same naming conventions, I don't need to change anything. Get left, get right, get data. They're all there. Well, of course, I need to change those to node star. Okay. So that should work as well. That should go as well. This should be node. This should be node. Anything else? Not apparently. Let me copy paste those as well. Q, stream. I should take all of those. Insert tree, CPP. Yeah. Okay, so let me copy this. Okay, so what I need to change is this definition. So let me open up tree age and copy those from there. So these in order, first order, print tree. What was I doing in print tree? Search for it. Oh, I think it's the, yeah, it should be the, wow, I don't have any print trees. That's a bummer. If I don't have this, why do I have this? Okay, I think, yeah, I'd better take this out. All right, so I should take those. I should put them into here. Okay, and I also have some private, yeah. It says, oh, pre-order, in order, recursive construct. I don't need recursive construct. There. Why am I doing this? Is I just want to be able to traverse the tree and print the contents of the tree. So I don't want to debug it and see and look at the structure every time I make a difference, make a modification. So yeah, that should work. So let me ask T, and of course I should put delete T. And also I should say T, what is this? Print, print pre-order, let's print pre-order. Okay, let's see if that works. Yeah, all right. But there's a, no, there's a mistake. So where do I have this mistake? Let me stop now. Okay, now my tree looks good. Oh no, it doesn't look good. Okay, let me see what is going on. Do I have everything? Why don't probably I made a mistake while I'm changing those bin S3 things. But let's see what's wrong. So this addition is done without, yeah, without something wrong. So let me go inside in here. If this root not null, yeah, that is the case. I go to the right and I edit and I iterate the temp towards the right. No, not temp, this root. Yeah, right is 8, that's fine. Oh, how am I, what is the temp? So the temp is 8. Oh, what am I doing is I'm returning here. Oh, okay, I understand now. So you see, the mistake is, well, since I'm making temp yet left, my next iteration is going to be on the left child of the newly added node. So I will be, so let me draw it to you. Okay, that's cool. So what I do, my mistake in here is I do this 5, 6, oh, not 6, 5, 4, 8. Suppose that I'm adding 9. So what I do is I always start. Oh, okay. Thanks for your warning. I do this every day, a couple of times. So, okay, so I start from here. I was trying to add 9. Okay, there is also 9 n in here. So how I do is I check the right child. I check the value 9 larger than 5. I go to the right. Okay, and I check. And if I find null, I make the addition. But my while loop, this t is iterating, you see. My while loop ends when the t becomes null. And how my code works is after I add, I make t go to the next once more. Now, when I do this while loop is going to iterate once more, and hopefully I was thinking like it's going to point to null in the end, and it will break out of the loop. But when I do this, it becomes the same with the data that I'm trying to add to. So it sees that the node that it recently added, it thinks that it is already in the tree, and it is thinking that it is not adding the node actually, and it is deleting this. So that's the problem. So what should I do is right after I add, I can quit. That would solve the problem. Okay. So why don't I do like right after you make the addition, turn. So you see, even when you are too careful about doing something when you are coding, there's always a possibility to do something wrong. Okay, so please do not go without testing. So you should test everything that's going on inside your code. Okay, so let me first try, see if that's working, and then I will, yeah, now it works. 5, 3, 2, 8, 9. Is it correct? Now, in order to check if it's correct, I'm going to make a very simple check. So what I'm going to do is I'm going to print an order. So what do we expect for this one to give us? Ta-dam! An ordered list, an ordered organization of data. So what we add is 58392, and you see we have added in quite arbitrary order. And when we set up the tree, we see that if we traverse it in order, it gives me the sorted version of the elements. And this is expected because you see the in-order traversal actually looks like a sorted array. So we have made this analogy. It mimics the sorted array actually. All right, so this was the addition. Enough talk about addition. Let's write a chat. Let's write a search function, and it should be easy. Let me write a search function. So I can actually copy paste. I can't believe I spent so much time trying to copy paste. Okay, so let's do it like again. You can do it in many different ways, and you can even return a node pointer when you search. You can do things like this, but I want this one to be as isolated as possible from the user. So I will just say true or false. So if a number is already inside the tree, I will say true. If it's not inside the tree, I will say false. So I'm making this one a bool. And let me call this contains. So I don't need to build up any node. And I don't need to, yeah, if the root is null, I can actually directly return false. And what else? Otherwise, I start from the temp. While temp is not null, I check the temps data. If my data is larger, I don't do anything but go to the right. If my data is smaller, I don't do any addition kind of thing, and I go to the right. I'm sorry, the previous step is go to the left, and this one is going to the right. And the last one is if they're equal. So if they're equal, I just want to return true. And in case I cannot find what I'm looking for, the temp will be null and I will go out of the loop. So I will say return false. Okay, and let me put this in my here. So let me get this one. Case. Let me put those traverses a little bit apart, and also these guys apart. So now, how should I do this? Let me do something like this. If T contains, let's do 8. If T contains 8, print in order. Or better yet, let's do like this. Let me test this one as well, if it's working or not. So if T contains 8, I do breadth first search. If T contains 7, I do print in order. So it shouldn't print in order, but it should print breadth first. Okay, seems like it's working. So it printed me the breadth first traversal. So that seems to be okay. Yeah, we have got the searching and adding underway. Now we continue with deletion, and the deletion is the real end of the level master. We need to think about it. How we are going to do when we are deleting. So first, let's plan about it, and then we can act. All right, so let me make another. Okay, so let's suppose that we have a tree. Okay, a binary search tree, of course. And let's suppose that, let me build a bigger tree. So let's start from 10. Let's put 5 in here. So 3, 1, 2, 7, 6, 9, and 15, 11, and 20. So first of all, let me ask you some things, some trivial questions. If I give you a binary search tree and I ask you to give me the smallest element in the search tree, what would you give me? Which one should you give me? So it should be actually the element in the very left corner. So your code will be very simple. You will start from the root, go as left as possible, and stop. And vice versa, for the biggest element, you should go right as possible, and stop. Right? Because it's not go left, left, left. When you are unable to go anymore, start going right. It's not like this, because when you start going right, it means that you are going to some element which is bigger than some other element. You shouldn't do that. So practically, let me show you what I mean. Suppose that these aren't there. Right? So still, the smallest element is on the leftmost side. It's not like go left and then go to the deepest leftmost element. It's not this. It is, however, independent of how many steps you need to go, independent of which level you need to go, you just go as left as possible. Not ever even once right. And when you hit the null, you return the element. This is the smallest one. Okay. So why am I explaining you this? Because now we will be removing something, and while we are removing something, this insight is going to be important. Now let's suppose we need to remove 5. So what will happen? First of all, we need to find 5. Okay, if there is 5 in this tree or not. Fortunately, we have written a contains function, which returns us true or false if it contains. Unfortunately, it doesn't give us the node itself. And then again, fortunately, even if were to give us the node, then we will still need something more. Because when we get rid of 5, which nodes will be which nodes would be modified, which nodes would be affected? So this and this for sure. Okay, because their parent is gone, they need a new parent. But also this one, because it is going to have a new child. Okay, and it will be something, one of those. So we need the parent as well. And if we get the pointer to the node, we would be able to reach those as well, because they are already in the left and right. But parent, we will not be able to reach parent. If we get the parent, on the other hand, we will be able to get all these 3 nodes references as well. So the parents, left or right child, according to which child is it, it is going to give us the we will be able to find out which child is it, and then we shall continue. And also, according to the child that the deleted node do belong to, I can get the left and right child again. So knowing about the parent is more important than knowing about the deleted node itself. So if you are going to write something which is going to search and return the node pointer, it's better to write which returns the parent. So I will do that. So once I find the parent, what is going to happen? Before going into that, let me highlight you one more thing. Now, all the things that I'm doing in here, that I will be doing in here, it's not in any way related to this. Right? It has got nothing to do with this part of the tree, because 3, 1, 2, 7, 6, 9, they have got nothing to do with those. All of them will be on the left-hand side of the root. Okay. Well, one way to do this, an easy but inefficient way to do this is, which I'm not going to do, without worrying about the parent and anything else, what I can do is I can get rid of this, and I can add this whole tree to this whole subtrees to this tree by writing a simple add method. It will look a lot like adding an integer, right? What it will do is, instead of constructing a new node, it will take the node address from the outside of the function, and it will make the addition. Since when I add this to the appropriate place in the tree, the children will be added to the appropriate place as well, because this is going to be kept. Let me show it to you. So now let's assume that I deleted this. And then I do add this one to the tree. How is going to happen? My tree looks like this now. 10, 15. Sorry, let me do it more properly. Uh, 15, 11, 20. Okay, so this is how my tree looks like. Now let's assume that you are adding 3, but with its children. You don't do anything about its children. You just take the 3 node and add it to the appropriate part. So where is it going to go? Here, right? So that is going to be 3, 1, 2. Now what you will do is you will add this one. The next 7 will go to the appropriate place. Where will it be? 7 is smaller than 10. It's larger than, well, I did something wrong, I think. Yeah, my tree is wrong. Sorry for that. This should be 4. Okay, this is 4. So now I'm going to add this 7. It is smaller than 10, larger than 3, larger than 4. So it should be the right child of 4. So let me add this. Right child of 4. So you see, when I'm adding 7, I'm adding it with its children. So it would go like 7, 6, and 9. All right. So please look at it. What I did was 2 additions. Is this still a binary tree? Yeah, there's nothing wrong with it. So the smaller elements are on the left-hand side, the larger elements on the right. And if you look at this, there's nothing which violates the binary search tree principle. And you see, I haven't touched the right-hand side. There's nothing about it. But this is inefficient. Why? Because what we do is we make 2 additions. I have shown you on a very shallow tree, but if the tree is 10 deep, then it would be, then you need to make 10 steps in order to, log n steps in order to find the appropriate place to do so. And it would be O log n. But on the other hand, well, even if you have 1,000,000 elements, how much that would be? It would be like for 1,000,000, it would be I don't know. Let's see how much is it. Okay, 1,000,000. Okay, it's 20 elements long. It's not that much. 20 steps is not that much. And it would be very easy to write this function. So, but again, if you think about doing it in place, it would be constant because we will do 2 or 3 link updates, it will be done. So independent of how deep our tree is, it will be done in constant time. So we always prefer constant time operations. So what we will do is we will do this by hand. Okay, so how it is done? Let me show it to you. So let me draw my tree once more. Okay, so it goes like this is going to be 10, this is going to be 11, no, not 11. And let's do it 15, 11, 20. Let's make it 5. Let's make this 3, 4, 1, 8, 6, and 9. Okay, and let's say that I am deleting this guy over there. So before deleting that, I need to have 2. It's better if I have 2 pointers because the first one will be showing this. The second one will be showing this. So this one will be parent. This one will be child. Why do I say I need 2 pointers? Because if I don't get 2 pointers, I need to, every time I need to make something, actually I need to do it once, but it's still additional code. Once I find the parent, I need to check if the child which I'm deleting is the left or right child. So the parent finding operation might already return me that. So I can do this. Okay, so I'm going to design my parent finding function so that it's going to return me this pointer and this child pointer, which this one. So you might be asking, how is it going to be possible? How am I going to return 2 things? Well, I will do it by just by referencing. Okay, you will see. Okay, so first node, we will do that. Second node, once we do it, what we will do? What we'll do is, of course, we are going to get rid of those. But before doing, we need to have to the 2 pointers to the left-hand child and to the right-hand child. Now, once we delete the node to be deleted, we will be left with these two. So what do we need to do is we need to select one of those, either left or the right. Both will do, but we will select one of those. Let's say that we select the left child. We will take the left child. Okay, so this guy over there. We'll take that guy. And what we will do is we will move this to here. So make it the child of the parent. Okay, so let me write it to you. Parents parent left child. Of course, that would change if I do from the right. Parent left child is going to be the left. And then what I will do is I will continue my pointer until the rightmost child of the left child. So why do I do this? Because I know something. This is the left child of some node, and this is the right subtree of some node. And I know all the numbers in the left side is smaller than all the numbers on the right-hand side. Or the other way around, all the numbers in the right subtree is larger than all the numbers in the left subtree. Which means, well, that means the place of all the numbers in this subtree is the rightmost side. Okay, we have talked about this in the beginning of our discussions. So the place of this right tree is just the rightmost side of this left subtree. So I can do only this. And it will work even if I do delete something from the right side. Okay, so let's do that. Let me do the same thing for the right-hand side. Okay, so I have gone too much. All right, so let's suppose that I'm deleting 15 now. This is the parent. So what I will do is I will get rid of those. So that would be, there would be the left child and the right child. And what I will do is, again, add the left to the parent's appropriate child. So what I need is, now you see, there are a lot of checks. If I'm deleting the left child of the parent or the right child of the parent, what I will do is, if you think about this one, the parent, there is the left and right pointers. I am going to use the address of whichever child is going to be deleted. So if I'm deleting the right-hand child, my find parent function is going to also set this address of this pointer. Be careful, this is double pointer. So I'm not going to return this, but the address of this. Okay, from the find parent function. Yeah, this is going to be connected to here, and I will go as right as possible, and this is going to be connected to here, and that will do the trick. It will work. Now there are two additional corner cases that we need to be careful about. The first one is, what if left or right child is null? Then if the left child is null, then I would add the right child right away, and it will be finished. If the right child is null, then I would not go to the rightmost element in the left child, and that is also straightforward. And what is going to happen if the deleted root is null, deleted node is the root? First of all, how can I understand it? Well, my parent function is going to return null because there's no parent of the root. And what if that one happens? Then if that one happens, the procedure is easy. The left child will be the new root, and the rest of the operation is the same. The right child is going to be added to the rightmost side of the root. Okay, So you see there are a lot of corner cases, and there is also lots of referential things going on. So it will take some time to implement this deletion operation. But when we implement it, it is going to be actually a constant type deletion from the binary search. So